Okay, we have talked about water as a material and how it behaves in different temperature regimes. And the most important one is what it behaves around 0 degrees Celsius. And you know that the density of ice is lower than that of water. And that's one of the reasons that aquatic life is thriving even in dead winters. And of course, we've talked about the Clapeyron equation that sort of underpins the relationship between pressure, the effect of pressure and temperature, and then how does it sort of seen uh, in the considerations for the enthalpy and the change in density, and how because these are natural properties, you can't really change much about that. You can only control the changes in pressure and temperature, which are synthetic, which are things that we use to control stuff. And that's again in that line uh, how ice skating is possible because of the formation of the liquid layer under pressure. And how does it form? You can get an idea from the Clapeyron equation. And taking forward from the Clapeyron equation, if we talk about the equilibrium between a condensed phase and a vapor phase, then you see that the change in volume, change in molar volume is not as important, and that you can simply convert it to the change in the vapor, I'm sorry, the volume, the molar volume of the vapor phase, and that slightly changes the equation where you can have the relationship between pressure and its corresponding changes in temperature when you consider the equilibrium between the condensed phase and the vapor phase, right? And in consideration of these two properties, the Clapeyron equation and the Clausius-Clapeyron equation, we see how it can be useful in a everyday practice. And there are many examples as such. And two examples that I gave you is the calculations of latent heat, which is an experimentally determined parameter, and that's based on these equations. And of course, the functioning of the pressure cooker, where increase in the pressure changes the boiling point to a positive number, and water can be contained at a much higher temperature without boiling, and that sort of helps you cook faster. Right now, let's having these preliminary information with us. Let's talk about something which is called phase equilibria, okay, which is the core of materials thermodynamics. And what is phase equilibrium? Uh, this is nothing but a kind of a map, okay, a map to understand the stability of different kinds of phases, right? In the changing situation of different thermodynamic parameters, thermodynamic variables, including pressure, temperature, composition, and things like that. Right. So there's a proper set of rules for that. I can only give you a basic idea of that while you do study in phase diagrams, specifically in your higher semesters, probably next semester, you'll get much hang of that. So to begin our discussions in phase diagrams, let's first define some of the terms which you might be using in the consideration of phase diagrams. Okay, so what we call phase, right? Um, I think from your lower classes, you might have understood that solid, liquid, and vapor, these are the phases. And in the domain of materials thermodynamics, that aspect, the definition of phase becomes slightly broader in the sense that you can you have things like carbon. Okay, carbon is different forms of electrodes. You have carbon as carbon black, you have carbon as graphite, and you also have carbon as diamond, right? And if you look at the outside of it, the physicality of it, and all of these things are typically what we call solids. Those are different solids of carbon. Okay, but then they are different phases. You know, they have different thermodynamic properties, different sets of um, free energy, Gibbs energy, which could change in the changing thermodynamic parameters. For example, in pressure and temperatures change, the stability of graphite versus diamond would change. You know, diamond is probably more stable in certain environment. Graphite is more stable in certain environments. So likewise, you can have different forms of liquid, although it's not very prevalent, but then you could still have different kinds of liquids. Of course, you have vapors. So the vapors for certain different types of liquids and many different types of solids, these are all typical phases and are distinct phases, right? Okay. So that we call is a physically distinct and a chemically homogeneous substance, right? So the substance is chemically homogeneous, that you know, they sort of not doesn't include anything else inhomogeneously, and it's a physically distinct surface. So much so that you know it's a physically it's bounded by surface. Okay, and there are additional sort of attributes of what we call phase is, you know, it's something that you should be able to mechanically separate. Of course, might be if it is some kind of a nanostructured phase. Now you might ask the question, can you separate it out? Well, you know, it cannot be separable by sieving, but then there are other ways to separate it out. So, you know, if that's a distinct uh, matter, uh, no matter how the size is, you know, what the size is, it can be nanometric dimensions, can be micron scale dimension, and it could be, you know, something else or a bigger one. So as long as, you know, it's mechanically separable, you know, it can sort of proceed. That's why I haven't put it in a definition as such, but then you can sort of use this to understand, to believe, you know, to sort of appreciate what exactly would be called phase. And they need not be continuous, right? So, for example, if you have a glass of water, okay, in that glass of water, you add an ice cube, okay, what happens? You'd call that, you know, it's a different phase of water, right? This liquid water and there is solid water. But imagine in that bowl of water you use two ice cubes. All right, now you have two ice cubes and water. So would that be three phases? No, because ice, you know, they are not continuous. Okay, but then, you know, it's the same substance, same physical substance, same physical attributes, and that's why it's single phase then. Okay, that the ice phase is single phase, and there is of course water. And likewise, you can take this discussion a little forward. Let's say you scrub ice, and then you have a heap of sort of ice dust, or, you know, or broken, or what do you call that? Broken ice, or, you know, or powdered ice or something, and then you put that in water. All these ice particles, small particles of ice, are also not continuous, okay, but they would still be called a single phase, you know, the ice phase. Along with that, we of course have water. So that's why the examples could be, you know, it could be solid, could be liquid, could be vapor. All of these things are phases, and when they are together, they could they'll be called multiple phases. Okay, and likewise, this alpha, beta, you know, or gamma or delta, these are typically denoted as solid phase, different types of solids of the same chemical composition. So these also are distinct phases, and when they exist together, they'll be called a multi-phase material, right? So that's the whole idea of phases, right? What we call phases, and then stability of these materials, okay, is understood by something which is called a phase equilibrium diagram, or simply called a phase diagram. Okay. That phase diagram tells you what are the effects of different thermodynamic variables on their stability, right? So that you want a specific phase to be stable in your material system, then you perhaps can choose the appropriate thermodynamic parameters to make that particular phase, the required phase, stable in a material system, right? Now, in that consideration, another important point comes up, which is called a component. And this is sort of related to chemistry. So the number of chemical substances necessary to define the composition of the system, right? Now, for example, I have a glass of water, and in that water I have crushed ice inside it, okay? What is the chemical nature of the substance that is contained in the glass, and how, and the minimum possible ways that I can define the chemistry of what is contained in the glass? You'd say that it's a two-phase system. It's agreed, because there is this water and there is ice, and there's not continuous ice. There's a, ice of the same type crushed together, and then it's dumped there. That's a two-phase system. But then, be it water or ice, you are able to define the chemistry of the system by a simple chemical composition called H2O. Okay. So as long as that is valid, so you would call that a single component system. So that's one number of components. Just one chemical formula is what you need to be able to define the whole system there. That's called the number of components in the system. Okay. So when we talk about a single component system, then we are essentially talking about the phase stability of water, okay, in any of its different phases, as per the given thermodynamic variables. For example, pressure and temperature are the normal ones we talk about. So it's and when the chemical components, the number of chemical components is just simply one, we call that kind of phase diagram as a single component phase diagram, which is what we are going to be studying at least in the first few lectures. The multi-component system is something we'll start, or the basics of the basic thermodynamics of that will start. The real diagrams of bi-component or two-component systems will be taken care in your fourth semester, right? So that's the number of chemical compounds, that chemical substances that will require, the minimum number that is required to define the system. That's the number of components. And now another term that's called degrees of freedom. Okay. Degrees of freedom is something that's, there are many thermodynamic variables that influence the stability of the system. Most important, most generic ones are temperature and pressure. Okay. Now the degrees of freedom means how many such thermodynamic parameters can be changed independently without bringing about a change in the stability of the system, the stability of the particular phase. That's called the number of the degrees of freedom, denoted by F. Okay. So if you go by the definition, the number of intensive independent thermodynamic variables. I think this is important to understand, that it has to be an intensive variable. Those are the ones which have driving forces to sort of affect the stability of the system. Right, so how many such intensive variables are there which can be changed independently? So, for example, if you talk about pressure and temperature, then how I can change, in which situation I can change the pressure and temperature without actually affecting the stability of, let's say, ice or alcohol or some other, for pentane or butane or something like that. What's the independence I have? Independence in pressure means, or independence variables mean, how can I change? How much can I change the pressure? That pressure is currently at 1 atmosphere. Can I change the pressure to 2 atmosphere, 3, 4, 5, 6, high? And if even after changing that, if my ice or something that I'm considering remains the same, then I would say that pressure is a degree of freedom. Likewise, can I change the temperature? Likewise, can I add more and more water onto it without changing something? That would then be called a degree of freedom, right? So these three important components, the parameters like phase, component, and degrees of freedom, they are clubbed together to give you a rule which is called the Gibbs phase rule, right? And that we can see here. So in the Gibbs phase rule, of course, given by Joshua Willard Gibbs, this says that the number of such intensive variables that can be found on phase rule is by this formula, which is F is C minus P plus 2. This is one of the most profoundly used thermodynamic equations in all of materials thermodynamic or elsewhere. Right? So you need to be able to find out what is the number of degrees of freedom from the C minus P plus 2, and C is the number of components, P is the number of phases plus 2. The derivation of it is not so trivial, but then that of course will require a few minutes to say, but then we'll give it a pass. All right, and typically we would see that this plus 2 relates to kind of temperature and pressure. Okay, now when we take this forward, for single component systems, we generally use this pressure and temperature as the most important, most common variables that sort of affect the stability of the system. All right, but when we talk about, let's say, multi-component systems, for example, the component systems of water and alcohol, or aluminum oxide and silicon dioxide, or aluminum oxide and chromium oxide, or iron and carbon. The phase diagrams of these two component systems are something that we use every day in our work, where pressure is not a variable. Okay, pressure, we typically operate in atmospheric pressure conditions, and these are open systems, and we don't consider pressure to be a variable, and we don't see that pressure has so much of an influence in the stability of these phases and the equilibrium of these phases. So that way, in all of material science, typically when we talk about multi-component systems, we don't consider pressure as an independent variable. Okay. We neglect pressure, that it has kind of no influence on the stability of the system. So in effect, we are left with 1, and that's what is given in this equation is F is C minus P plus 1. Okay, that's typically what we use in material science. And more importantly, when we use that in multi-component systems, right? That's the thing we use. But to extend our discussions, let's say that we'll go with this one for the single component system, and see how it sort of behaves, right? So let's go and see how a typical phase diagram would look like. Okay, this is a picture I picked from the what's that? The Paul book, the Cambridge book, Atkins, Paul Atkins book. It sort of gives a imaginary phase diagram, right? And you would see that. Let me introduce you to what typically would be called a phase diagram. Here, we are talking about a single component phase diagram. That means the chemical nature of what is contained here is just single. You can define the contents of all of these things by one chemical formula. So that's a single component system. And here, what we're trying to see is it's kind of a map where we have two variables, which is pressure and temperature. Okay, and what we're trying to find out here in these regions is the stability of each of these phases. Okay, now what kind of phases we have here? We have the alpha phase of whatever solid that we're talking about, solid or liquid or material that we're talking here. It's alpha phase of the material. This is the gamma phase, this is the beta phase, this is the epsilon phase, and this is the delta phase. It might show that this could be a liquid phase, this could be solid, this could be a liquid, this could be a gaseous phase, depending on various other parameters, which of course you can guess. But these are phases. These are the number of phases here. All right. And this is, if this is the alpha phase and this is the gamma phase, um, for the alpha phase, this is what is called the primary phase field of alpha. Okay, I'm not naming what is alpha and what is this material, but this is the generic one. If this is the alpha phase, this alpha phase, or the stability of this phase, is bounded by this area, and this area would be called the primary phase field of the alpha phase. Okay. What does it mean, bounded by the area? It means it's a combination of coordinates. Coordinates of what? Coordinates of pressure and temperature. When you talk about this point is a coordinate identified by pressure from this reading and temperature from this reading. Okay, so when I say it's bound by the region, that means it's bound by a collection of coordinate space of the pressure and temperature, which are the variables, the thermodynamic variables. So this region is called the primary phase field of alpha. Likewise, you have a gamma phase here, which is bound by the region this. That means bound by the conditions of pressure and temperature like this. Right? Likewise, you have the epsilon phase bounded by this region, the beta phase bounded by this region, and you have a delta phase bounded by this region. All right. Now, we can do some calculations here. Now, if you go back to this equation, F is C minus P plus 2. Okay, let's apply that here. F is C minus P plus 2. Now, we need to always figure out what is the F number here. The answers are written here, but let's go and do the calculation. F is equal to C minus P plus 2. What is it? C. C is the number of component. C component is 1, because this is all uniform chemically. Okay, so this is a single component system that we are talking about. So C is 1 here. Then again, C minus P plus 2. P, how many phases are there in this region? In the primary phase field, it is only alpha phase. There is no other phase coming into picture. All right. So the number of phases is also 1. Okay. So that is C minus P plus 2. That is 1 minus 1 plus 2. That's the number of, that is 2. That's the number of degrees of freedom is 2 here. All right. Now, what does this mean? This degrees of freedom is 2. That means in this region, in the coordinate space bounded by this region, I can change two independent variables independently. I can change these two thermodynamic variables independently. What do I mean by that? That means I can be here and increase the pressure or decrease the pressure, right? And I can also here increase the temperature or decrease the temperature. Okay, without bringing any change in the alpha phase. That means even if I change the pressures by increasing or by decreasing, even if it change the temperature by increasing or decreasing, alpha phase is going to remain the alpha phase. It's not going to change. Right? The means
So that alpha phase, beta phase, they are just named like this, or there is any particular thing like this will be the alpha phase, or
yeah, well, yeah. What I'm saying is this example is a generic example. All right. Instead of alpha phase, you can have solid here. Gamma phase, you can have a liquid here. Beta phase could be something else. It can be solid, but then a slightly different one. We'll talk about that. So we can have a name for alpha phase. We can call, some gamma phase is austenite somewhere, alpha phase is something else, beta phase is something else, a liquid phase we can call, this is the epsilon phase, the vapor phase, we can call like that. Or delta is the vapor phase, we can call like that. What I'm giving here is a general. Instead of alpha, I can call solid. It'll be still the same. All right. What I'm trying to say you is that here, as you calculated also, that if the degrees of freedom is 2, that means I can have two thermodynamic variables I can change, and the alpha phase will still remain alpha phase. right? And and when I say that I can change pressure and temperature, those two thermodynamic variables, I mean that I can change those temperature and pressure within the coordinate space, right? That means when I change the temperature from here to here, I go right. It means I increase the temperature. The alpha phase will still remain alpha phase, okay? But when I come here, when I cross here, this temperature, then at this pressure, if I start increasing the temperature, it'll still remain alpha phase, but it's about at this point that I'll start getting the first formation of the gamma phase. All right, and I keep going to the right, it might so happen that all of my alpha phase will be converted to the gamma phase. So when I'm talking about, I'm first seeing the first traces of gamma phase as I keep on increasing the temperature across this line, or when I touch this line, then I'm not in the primary phase field of alpha anymore. It means I'm entering into another territory where the laws are governed by the gamma phase. This is the most stable phase here. That means like alpha is here, the gamma phase here is is within its primary phase field, which is bound by the pressure and temperature coordinate space spanning across this area. So here, the corresponding pressures and temperatures of this area, that becomes the primary phase field of the gamma phase, right? When I keep on increasing temperature, I'll still have alpha phase, but then when I cross this line, I come to the gamma phase field. So this alpha, excuse me, this alpha phase now swiftly converts to a gamma phase. That's called the transition. This can be a solid and this can be a liquid. I'm just naming here alpha and gamma. All right. So this is called the phase transition. Likewise, you can have a beta phase here. So as long as in a single component system and single phase system, you always have 2 degrees of freedom. Meaning you can change those two thermodynamic parameters independently without actually bringing any change in the primary phase field. So you see here is that this is the primary phase field of the alpha phase. This is the primary phase field of the gamma phase. This is primary phase field of the epsilon phase. This is for the beta phase, and this is for the delta phase. So these regions are single phase, single component regions, and by virtue of this rule, you'd see that you can always change pressures and temperatures, of course bounded within a range. You can change those thermodynamic parameters without causing any transformation of that particular phase. All right. Now, going back to the discussions where I said that we can increase the temperature from here to here and then convert it to the gamma phase, and when we come in, when we are in contact with this line, okay, then you start forming the first phase of the gamma. Right? That means when we are at this point, okay, then the alpha phase and the gamma phase are in equilibrium. Okay, if you talk about the molar free energy of each of these phases, here is where the molar free energy of alpha and the molar free energy of gamma are the same. All right, now that means at this line, so the region of coordinate space along this line is where I have two phases in equilibrium. So going back to this formula, what is P here? What is P in this line? Since I have two phases in equilibrium, I would say that this is a biphasic region. All right. So the number of phases that are present here are, that's 2. Now, what's the number of components, chemical components? That is still 1, because alpha phase and gamma phase are chemically similar. It's the same phase. I mean, is the same chemical substance. So the number of components that I have is a single component. As I said, then it's whole of this diagram is a single component diagram. Right? So along this line, I have two phases and one component. So if you apply this rule here, F is C minus P plus 2, that is C, the number of components is 1, minus P, two phases are in equilibrium, plus 2. That means 2 get cancelled. What I get is only 1 here. That means the number of degrees of freedom I have here in this two-phase equilibrium line is 1. What does that mean? That means I can change only one parameter. But you must pay attention to the fact that it is not about simply changing one parameter and not bringing about a change in equilibrium. It's about independently being able to change one parameter. Okay, now here I can still come, I can change pressure here, I can decrease pressure. I can decrease pressure here, I can still be in the equilibrium between alpha and gamma phase. All right, but when I do that, I do not have any control on the temperature. All right, so I can change, I have the liberty to change either pressure or temperature, one at a time. And if I'm changing pressure at my will, this will adjust itself, okay, and you would still be in equilibrium. If I have the temperature lever, then I can use the temperature lever, or I can change the temperature, but then I can allow I can allow the pressure to be adjusted so that I can remain in the equilibrium. So the idea of degrees of freedom 2 here in the primary phase field and the degrees of freedom 1 here in a two-phase equilibrium line that's why that they are different. They're different in the sense that here you can change pressure and temperature, but you still are in equilibrium in the sense that alpha phase remains alpha phase. But then here you don't have that liberty of changing both the parameters all at once. You can only change one parameter. Okay, either of that, either of pressure or temperature, you can change, but you can still maintain the equilibrium between alpha and gamma phase. So the idea is like this, you can have a two-phase equilibrium here. You can have a two-phase equilibrium here. Here this equilibrium is between the epsilon phase and the delta phase. This one is the equilibrium between the beta phase and the delta phase. This line is the equilibrium line between the beta phase and the alpha phase. The whole idea is that when you're talking about this line, okay, the line, you know, which is connecting both, the number of phases that it's connecting to would be you know, that many phases in equilibrium. So here this line, it's connecting this phase as well as this phase. That's why it's a two-phase equilibrium line. So likewise, you have a two-phase equilibrium line here, 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 and also here. All right. Now, so in all of those lines, you have univariant lines. These are univariant in the sense that only one thermodynamic parameter can be varied. All right. So this is what is given here. F is 1. Now consider another point in the diagram. So what we are left with, we are here, you know, we have covered all of the diagram because this is a primary phase field, this is this, we've entirely covered it, only except for the lines. Now in this univariant consideration, we have almost you know, talked about this line, these, and these. We are just left with these 3 points. All right, and this point is something which is you know, is in contact with 3 different phases. This is the delta phase, this is the beta phase, and this is the alpha phase. All right, so exactly at this point, the number of phases in equilibrium are P is equal to 3. All right, and how many chemical components that we have? You know, it's the same one, single component system. So if you apply this principle here, this is, I'm sorry, the chemical component is 1 minus number of phases is 3 plus 2, that is 3 minus 3, that is 0. That means at this point you have no freedom. You have no freedom of what? You have no freedom of changing either the pressure or the temperature or any thermodynamic variable. Any change in any of the thermodynamic variable would take you away from a three-phase equilibrium. Right, that's important. That any change in the thermodynamic variable would take you away from the three-phase equilibrium. Either it will go into a single-phase system or it will go into a two-phase equilibrium line, but it will not be in this triple point, which is a three-phase equilibrium point. So that's why this is called an invariant point. Now we call it a univariant line here, and this is called the invariant point. And normally we use this the language of triple point in phase diagrams for about this point. All right. So likewise, this is the point where we have equilibrium of three phases. Likewise, we have it here, and this point and this point are invariant points, and that's where you cannot have a change in the thermodynamic coordinates, without actually bringing a change in the stability of the system. Talking about this system, this is a theoretical construction of a phase diagram where this actually doesn't happen anywhere in a phase diagram. Why? This is technically incorrect. This, you cannot have a diagram like this. Why is that? Because this, we talk about this point, it's a quattro point, or I'm just making up. There is nothing called a quattro point. But then just, this theoretical diagram, which shows that this point or this coordinate space has where four different phases are in equilibrium, right? If you use this formula, this is C's component is 1, plus 2 is 3, minus 4 is minus 1. Okay, the number of degrees of freedom being minus 1 doesn't make any sense, right? So this one actually cannot happen. This is P is 4 is forbidden, right? So this is how we understand a phase diagram, and that's how we sort of read a phase diagram, as to what all these axes are important, or what these lines are important, and all that. So we'll stop here. We'll take a break, and then convene again in five minutes or so. But before I drop it, are there questions that we can talk about? I'm opening up for questions. Yeah, any questions? We can take one or two questions and then drop it and go to the next one. Yeah.
Hello, sir.
Yeah.
Hello, sir.
Yeah.
Sir, if we consider alpha phase within the coordinate area, sir, then what will be the value of the phase? Means that what will be the value of P?
Within the coordinate area, that's the single phase, right?
Yes, sir.
Yeah, that's P. That P is 1.
And if we consider between two phase, that is between equilibrium. So
Yeah, when we are considering when we are considering this, only this line,
yes,
right?
sir.
See, this line is where two phases are in equilibrium.
Yes, sir.
Okay. So the number of phases that we are considering here is two phases now. It
Yes,
is
sir.
single phase. This is two phases. This line, all of this line is two phases. This is again a single phase. This is single phase. This is all of this line is two phases. Again single phase. Single phase. Single phase. This line is two phases. Okay.
Yes, sir.
Two phase. Two phase. Two phase. This point is three phases.
Yes,
All
sir.
right.
Yes, sir.
Yeah. Yeah. Any other questions? No.
So can you just again explain that if f is equal to 0, what is that means? What is that signifies?
F is equal to 0. Okay. F is equal to 0 meaning When we say F is equal to 0, that means, say, okay, how do I say that? We have you have a temperature and pressure where you are able to have equilibrium between three phases. All right. Now, if that temperature changes, let's say you have an equilibrium at 1 atmosphere and 25 degrees Celsius. That's where you have alpha, beta, and delta phase all at existence at this point. All right. Now, if you make the temperature slightly higher, that means you make temperature from 25 degrees Celsius to 26 degrees Celsius. All right. That means it completely detaches from the three-point equilibrium, and then it can even come to the single point region or the biphase equilibrium region. But then by virtue of the change in the temperature, you're losing the equilibrium between alpha, beta, and delta, and you might end up being in the equilibrium between beta and delta itself, but you'll not have alpha phase in equilibrium. Do you understand what I'm saying? That means you lose the equilibrium between three phases. You might end up being in equilibrium between two phases or any of these two phases, depending on what's the thermodynamic parameter that you're changing. Or it might even so happen that you will come to a single phase equilibrium area. Okay, if you drop the pressure, for example, you're here and then you're decreasing the pressure. That means from this point, you are dropped into here. All right, now you are in a single point region, a single phase region. So the degrees of freedom of 0 at this point means that you cannot change anything. You cannot change any of the thermodynamic parameters if you want to be in equilibrium between these three phases. All right, that means you have no liberty. You have no liberty of changing the thermodynamic parameters. That's what is called degrees of freedom is 0. That's why it is called invariant point. These points are called invariant points. That means you cannot vary anything if you want to be in that equilibrium position. Make sense?
Yes, sir. Yeah.
Yeah.
हेलो सर.
Yeah.
सर वो जो फॉर्मूला आपने बताया था सर, वो एफ इक्वल टू सी माइनस पी प्लस टू एंड सी माइनस पी प्लस वन, सर वो कैसे वो दूसरे केस में प्लस वन हो जाएगा, इसको एक बार और एक्सप्लेन कर.
Yeah, for this Gibbs phase rule.
Yes, sir. पहले में प्लस टू दूसरा प्लस.
Yeah, so the derivation of it is slightly mathematical one. You know, we could take up in another class if you like. It's a slightly longer one, but then I think there's no point getting into that at this point. If you can just remember this one, I think it's fairly straightforward to remember. This f is c minus p plus 2. You know, we'll go with that. And just a little variant from that is, you know, when we don't have too much to worry about the pressure, or pressure has no effect on your systems, then it's simply c minus p plus 1 is 2. Or you can simply say that, you know, you can go back by saying that, you know, f plus p is c plus 2. The number of phases and number of degrees of freedom, and that's equivalent to the number of components you have plus the number of thermodynamic parameters that you can change.
सर बट यहाँ पे लाइक अगर ये प्रेशर इज नॉट अ वेरिएंट, तो सर मतलब इसका मतलब क्या हुआ. लाइक आपने बताया कि लाइक मटेरियल साइंस में हम लेते हैं प्रेशर कांस्टेंट, बट अगर प्रेशर को हमने चेंज किया तो वहाँ पे सिचुएशन चेंज हो सकता है. फिर वो कैसे इनवेरिएंट होगा, फिर उसको चेंज करने पर सिचुएशन चेंज हो रहा है.
Yeah, you're okay. Hold on a moment. You're talking about this formula, or you're talking about pressure changes here?
नहीं सर, फॉर्मूला वाला. सर फॉर्मूले वाले में जो वो लिखा है सर, प्रेशर इज नॉट अ वेरिएंट, तो सर इसका मतलब फिजिकल सिग्निफिकेंस क्या है?
No, yeah. You're a very important point you have raised. So that's why it is written. You write. You see something which is written here. When in material science, when pressure is not a variant. Okay, I don't know it is technically correct or not, the language of it. What I'm trying to say is that in most of the material science experiments or the manufacturing, fabrication, or you know, synthesis that we do, we generally do not change pressure, right? The kind of things that we deal with, ordinarily pressure is not really a problem. That's why pressure is something which doesn't bother us. right? That's why you take one of those thermodynamic parameters out of it and redefine the number of variables that you can change in different forms of equilibrium, phase equilibrium. We redraft it as C minus P plus 1. But be it material science, solid state physics, chemical engineering, or anything else, if you have a pressure that has a influence on phase stability, this formula would not apply. This is the basic formula. F is C minus P plus 2 is the base formula. It's only a borrowed formula from there, suiting to only material science needs. When pressure is not a variant, you can use this one. Okay, this is sacrosanct. This is a corollary of that. All right.
ठीक है सर तो यहाँ पे सर कहा जा रहा है कि लाइक प्रेशर कांस्टेंट रख के सर जो भी काम करना होता है एज अ मटेरियल फील्ड में हम करते हैं, बट सर अगर वहाँ पे प्रेशर चेंज करे सपोज, तो फिर सर जो इक्विलिब्रियम वगैरह है वो तो चेंज हो जाएगा, फिर हम कैसे
Just yeah, let me tell you. See, some of the materials that some people produce. I mean, I also have been involved in some kind of work like that. You produce some materials where it gives you a different phase when you when you apply pressure on it. All right. In that circumstance, why would you use this formula? You can come back to the original formula, right? Because see, when we said that when pressure has no effect on it, all right, then you'll use some formula like this, which is fairly common, that many of the stuff that we do, pressure has no effect on it. But then, as you said, if we are working on materials where
तो सर सेकंड वाले को ऐसे भी हम कह सकते हैं लाइक व्हेन प्रेशर इज कांस्टेंट, ऐसा हम कह सकते हैं सेकंड वाले को.
well I wouldn't say when pressure is constant. I would say when pressure is no effect. All right. Even say if I do something which is not influenced by pressure, but then when I do an experiment in a changing pressure environment, all right, then I would be forced to apply this formula when you say that instead of when pressure is not a variant, okay, and you say that when pressure is constant, then it technically doesn't sound good, although what you mean is the same thing. When pressure is not a variant, with this, what I mean is that when pressure is no influence. Okay. In a way, when I say pressure is not a variant, meaning pressure is constant, that if that kind of a message it gives, it is okay, but it is slightly inappropriate. In the sense, maybe this is also a wrong statement. When pressure is not a variant, instead of that, I think I should have written when pressure has no influence on the system, which is actually meant by this. The pressure doesn't actually, an important variable in the material system that we're talking about. When pressure is not a variant, then we come back to here. But anything that we do, be it material science or solid state physics or chemical engineering, when pressure has an effect on the material system or material stability or stability of each of these phases, then you're not supposed to be using this equation. You must be using, you should be using the base Gibbs equation.
Okay.
Right?
Okay.
Okay. So I'm stopping the recording here. We will take a couple of minutes break and reconvene. Is it okay?